Dear students, last time we have seen statement of Lewis distribution law and its limitations. Today let us see Henry's law. Henry's law is a form of distribution law applicable for distribution of a gas between a gas and a suitable solvent, in which the gas under examination dissolves to some extent on applying pressure. Let us see at first the statement of Henry's law. Henry's law states that at constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas above it. Let me repeat it once again. The statement of Henry's law: at constant temperature, the solubility of a gas in a liquid is directly proportional to the pressure of the gas above it. We can explain Henry's law in following way, taking an example of distribution of CO2 gas in water. Let us suppose we have taken 500 ml distilled water in a Hampel gas pipette. Hampel gas pipette is designed for analysis of gas here. Let us suppose we have taken a Hampel pipette, filled it with 500 ml water, and we have filled CO2 gas above water in Hampel pipette using manometer or pressure gauge. Manometer. And the pressure which we have applied in this case is, let us suppose, 4 atmosphere. 4 atmosphere. We will find that when we keep this assembly, that is Hampel pipette containing CO2 gas and distilled water, in thermostat at constant temperature like 298 Kelvin for sufficient time. Let us suppose we have kept Hampel pipette containing CO2 gas and water in contact with each other in thermostat for half an hour. We will find that CO2 distribute between CO2 gas and H2O, and equilibrium is established. A dynamic equilibrium is established in this case. A dynamic equilibrium which exists between the gaseous CO2 and water, the CO2 dissolved in water. Actually, the equilibrium, we can write the chemical equilibrium which exists in this particular case by this expression CO2 in H2O. So let us suppose equilibrium is established. There is no any further distribution of CO2 in water and CO2 gas. A stable equilibrium, chemical equilibrium has been established. Let us suppose we have determined the concentration of CO2 dissolved in H2O by some suitable method, and we have also determined the concentration of CO2 gas above water. Let us suppose the concentration of CO2 gas dissolved in water in this particular case is C1, and the concentration of gas, let us suppose C1 is concentration of CO2 in water, or rather liquid phase, and C represents the concentration of CO2 in gas phase. On applying Henry's law to this equilibrium, or let us apply law of mass action to this equilibrium, we will find that here, when we apply distribution law to this equilibrium, CO2 gas in equilibrium with or other CO2 in water in equilibrium with CO2 gas. When we apply distribution law to this chemical equilibrium, we find that here C upon C1 is equal to K, where K is the equilibrium constant. Now, as we know, the concentration of any gas is directly proportional to its pressure. C is directly proportional to P. So we can have, in this case, C is equal to K into P, where K is proportionality constant, and here this K is known as Henry's constant. So we can write this expression, rearranging this expression like this: K is equal to C upon P. Here K is known as Henry's constant, and this expression C is equal to K into P is known as Henry's law equation. Henry's law equation holds good for dilute solutions like that of distribution law. So with this, I hope you have understood what is Henry's law. So in general, we can apply Henry's law to distribution of any gas like NO, NO2, SO2, CO, CO2, NH3, so on and so forth. So, in short, Henry's law governs distribution of a gas between a gaseous phase and a suitable liquid phase at constant temperature. So, what is the application of Henry's law? There are certain important applications of Henry's law. So, whatever soft drinks which we drink in summer days, like carbonated beverages and some other soft drinks, contain dissolved CO2 in it. So, the dissolution of CO2 in that case is one of the important application of Henry's law. With this, I hope you understood what is Henry's law and how it is useful for dissolution of CO2 gas in the manufacturing of carbonated beverages. With this, let us switch over to the next important point, and the next important point is the study of association of solute in one of the solvent during distribution, or in other words, how the distribution law modifies when the solute undergoes association in one of the solvent. We have seen at the time of studying limitations of distribution law, whatever mathematical expression of distribution law which we have seen, C1 upon C2 is equal to Kd, is strictly applicable when the molecular state of the solute under examination remains constant in both the solvent. However, sometimes what happens when solute goes in either of the solvent during distribution, it undergoes certain changes. And in that case, when solute undergoes certain changes, we cannot apply or whatever normal Merz distribution law, C1 upon C2 is equal to Kd, is not applicable in that case, or is invalid in that case, because whatever solute which undergoes certain change in either of the solvent do not exist in normal state, it exists in some another molecular state, and we know the Nernst distribution law is strictly applicable when the molecular state of the solute remains constant, remains same in both the solvents. So let us see how can we modify, or how Nernst distribution law is modified and applied to the distribution of such a solute which undergoes association in one of the solvent. Let us take an example of association of benzoic acid in benzene. Here what happens when we take benzoic acid solution in benzene in a separating funnel and mix it with distilled water and set vigorously, we find that benzoic acid distribute between two immiscible solvents, in this case benzene and water, and an equilibrium is established. When we determine the concentration of benzoic acid in benzene layer and concentration of benzoic acid in aqueous layer, that is water, we find that the concentration of benzoic acid in benzene is very high uh, as compared to the concentration of benzoic acid in water. And at the same time, when we study the molecular state of the benzoic acid in benzene layer, we find that benzoic acid in benzene layer undergo association. Two molecules of benzoic acid come together and forms the associated species, and the associated species which forms in benzene layer here is known as a dimer. So let us see how normal distribution law is to be modified in this case. The modification of Nernst distribution law is essential unless and until we modify it to certain extent, we cannot apply normal dust distribution law to the equilibria existing in the solvent in which the solute has undergone certain change as per its molecular state is concerned. So let us see how can we derive an expression for modified distribution law when solute undergoes association in one of the solvent with some general example. Let us suppose we have some solute X and the molecular formula of the solute X remains same in water. On the contrary, when solute X goes into the organic solvent which is immiscible with water, n number of X molecules come together and forms Xn. So let us show the equilibria, various equilibrias existing in this case with the help of one simple diagram with which we can very easily explain or we can very easily derive modified Mohs distribution law. Solute X, here it is solvent two, or we can say phase 2. Here it is solvent 1, solvent 1 or phase 1. Solute X, it distribute between these two immiscible solvents, solvent 1 and solvent 2. Solvent 1 is water. Let us suppose here solvent 1 is water and solvent 2 is some organic solvent immiscible with water. So solute X, it distribute in between these two immiscible solvents, solvent 1 and solvent 2, and in solvent 2 it undergoes association. X and X in equilibrium with X young. So here X represents the normal state of the solute in solvent 1 and X in equilibrium with Xn represents the chemical equilibrium existing between single molecules, n number of single molecules of X and Xn associated species, associated molecules in solvent 2. Hope you have understood how solute X distribute between two immiscible solvents, solvent 1 and solvent 2. In solvent 1, solute X exists in normal state. On the contrary, when solute X goes into the solvent 2 or phase 2. In phase 2, solute X undergoes association. N number of X molecules come together and forms associated species Xn, and Xn is in equilibrium with the X n number of single or simple X molecules existing in the solvent 2. Let C1 represents the concentration of solute X in solvent 1. Let C1 is concentration of solute, normal solute existing in normal molecular state in solvent 1. The concentration of solute which exists in normal state in solvent 1 is C1. So let us suppose C1 represents concentration of solute in solvent 1 or phase 1, and C2 represents the total concentration of the solute in solvent 2. Let C2 represents total concentration. Total concentration includes both very small number of single molecules existing in normal molecular state in solvent 2 and the large number of associated species existing in Xn state or in associated state, modified molecular state in the solvent 2. So C2 represents the total concentration of the solute in solvent 2 or phase 2. Once we understood this, what is C1 and what is C2? Let me repeat it once again, because here it is very important to understood what is C1 and what is C2. C1 represents concentration of solute in solvent 1, and we know that in solvent 1 solute remains in normal state. On the contrary, in solvent 2 solute undergoes chain association, in this particular case undergoes association and form the associated species Xn. It is very important to note here that in solvent 2 most of the single molecules which goes in solvent 2 undergo association and forms the associated species Xn, and very small number of X molecules remain in normal state, or we can say simply in X state. Hence the total concentration of both X and Xn, the associated species in solvent 2, is C2. Let us apply law of mass action to the chemical equilibrium existing in solvent 2. The chemical equilibrium existing in solvent 2 is Nx is in equilibrium with Xn. So let us apply law of mass action to this equilibrium. Xn in equilibrium with and X. Equation number, this is a chemical equilibrium which shows equilibrium between what the associated molecules Xn and the non-associated or simple molecules X existing in solvent 2. When we apply law of mass action or the law of chemical equilibrium to this equilibrium, we get K is equal to concentration of X to the power n upon concentration of X m, where K is equilibrium constant. Mind well, equilibrium constant of the equilibria as shown in equation 1. This is equation number 1. Here it is very important to remember that here K do not represent the distribution constant or the partition coefficient or distribution coefficient. Here K represents the equilibrium constant of this equilibrium, okay, existing in solvent 2. Now, once we understood this, we will find that the concentration of X we can calculate from this equation, equation number 2, the concentration of single molecules X. How? Simply rearranging equation number 2 like this. X is equal to n root of K into concentration of X n. Hope you understood how we have got this expression. Okay. So when we rearrange this expression, X to the power n will be equal to K into concentration of associated species, and when we take nth root of X, we will get X is equal to nth root of K into concentration of associated species X m. Let us suppose this is equation number 3. When we look at this expression, we see that we can write this expression in another way. Nth root of K into nth root X n. When we look at this, we find that nth root of K is a constant because here n is an integer and K, the equilibrium constant of this equilibrium, chemical equilibrium, has a certain value, has a different value, or in other words is constant at a particular constant temperature. So we can write this expression: X is equal to concentration of X is equal to constant into nth root of X m. Equation number 4. Okay. When solute exists largely as associated molecules, which is true in this case, at high dilution, the concentration of associated species, that is X n is taken as equal to C2. In other words, the concentration of associated species in solvent 2 is equal to C2, or in other words, what we assume in this case, as the large number of molecules undergo association and very small number of single molecules exist in solvent 2, the total concentration C2 represents the concentration of associated molecules in solvent 2. Now, substituting C concentration of associated molecule is equal to C2 in equation number 3, what we get, X is equal to, that is concentration of single molecules, X is equal to n root of K, or in other words, simply constant into C2. That is here the n root of C2. So instead of concentration of molecular species Xn, what we did, we have substituted the concentration of molecular species Xn by C2 in this expression. So what we get, X is equal to concentration of X is equal to constant into n root of C2. Let us suppose this is equation number 5. We know that distribution law is valid for concentration of similar molecular species in the two phases. Hence, we have C1 upon X is equal to constant C1 upon concentration of X is equal to constant. And when we substitute X is equal to constant into n root of C2 in this expression, we get C1 upon n root of C2 is equal to constant into constant. So let us have another constant for this, constant into constant, K D. So at last, what we get, C1 upon n root of C2 is equal to K D. Equation number 6. When we look at this expression, you will find that this expression is applicable to the distribution of solute which undergoes association in one of the solvent, such as solvent 2 in this case. And in this way, we have seen how Nernst distribution law, normal Nernst distribution law, C1 upon C2 is equal to Kd, modifies when solute undergoes association in one of the solvent. This expression, the last expression, we can, for our understanding, say that the modified distribution law, when solute undergoes association in one of the solvent, is very, very useful, very, very important for determining what the molecular state of the solute in either of the solvent when the solute distribute in between a pair of immiscible solvents in contact with each other. This expression can be further modified and written in the form of logarithm. In that case, we can say that the logarithmic form of modified Lewis distribution law and the modified Lewis distribution law in this particular case is log C1 is equal to 1 upon R into log C2 plus log KD. In other words, when we take logarithm on both the sides of equation number 6, what we get? We get log C1 is equal to 1 upon N into log C2 plus log KD. When we look at this expression, let us suppose this is expression number 7. Expression number 7 is representing an equation of straight line of the form y is equal to mx plus c. Equation of a straight line of this form. What does it mean? It means that when we plot a graph between log C1 and log C2, a straight line graph is obtained, will be obtained, and the slope of that straight line graph will be equal to what 1 upon m, and from that slope we can find out what the value of n. What is n? The number of single molecules undergoing association in solvent 2. So in this way we can find out how many number of single molecules come together and forms the associated species in solvent 2. So this is one of the important application of this logarithmic form of modified distribution law. Another important application or another important use of this equation is we can find out the numerical value of partition coefficient Kd or distribution coefficient Kd from graph. Because in this case, we find that when we plot a graph between log C1 and C2, the y-intercept of the graph will be equal to log Kd, and from that log Kd, we can very easily find out the numerical value of distribution constant Kd. In this way, we have seen how Lewis distribution law modifies when one of the solute undergoes association in one of the solvent. And the best example with which we can understand this association of certain solute in one of the solvent is distribution of benzoic acid between benzene and water. Here we will find that when benzoic acid goes into benzene, it undergoes association and two molecules of benzoic acid C6H5 COOH come together and forms an associated species known as dimer. So with this, I hope you understood how most distribution law is modified when solute undergoes association in one of the solvent. With this, I stop here. Next time, we will see how Nernst distribution law modifies when solute undergoes dissociation in one of the solvent. Thank you. Thank you very much for listening carefully.